Lesson 26 is comprised of 5 slides, which introduce a relatively new design procedure for the design of columns called the direct analysis method. Now, you're not responsible for this lesson, lesson 26, and I'll go through it quickly. Basically, this method's a new method for analyzing columns and beam columns. As mentioned in lesson 12, that the buckling capacity of a real column will deviate from the idealized Euler column for several reasons. That's including, the end conditions other than pin-pin, inelastic behavior, initial curvature, and eccentric loading. And what the direct analysis method does is it attempts to better quantify the effects of these deviations. And it does so through what are called notional loads, also adjustments on material stiffness, and also the ability to do second order analyses. One important thing is that the direct analysis method assumes an effective length factor of 1. Now, notional loads are loads that really don't exist. But basically what happens is we apply these notional loads to the structures that will basically push the structure over a little bit such that it'll begin to mimic the imperfections that we normally have in columns. And when buildings are erected, the structural steel is actually allowed to be out of vertical, out of plumb per story by a ratio of 1/500. And this is actually specified in the AISC steel manual, but it's in the Code of Standard Practice, which is section 16.3, instead of 16.1, which is the specifications. So if you have a story height of 15 feet, then the out of plumbness is limited to about 0.36 inches or 3/8 of an inch. And as you know, if the column's not perfectly straight, you're going to have then a reduced buckling load. So again, by applying the notional load, the structure then gets analyzed with this lateral displacement that may be actually present in the actual structure. So again, note, when we analyze a structure, we're assuming that all members and joints are perfectly aligned. Now this slide just shows the magnitude of the notional load. And what you see in this procedure, the direct analysis procedure, is this alpha term. And that's a correction factor if you're using allowable strength design. So in LRFD, it's always going to be 1. And so you calculate a notional load for each level, and what it's going to be is a certain percentage of the gravity loads that are applied at that level, and it turns out to be 0.2%. And then another thing they do in the direct analysis method is adjust the stiffness, and do that by using a factor of 0.80, which takes into account the reduced stiffness that you get from residual stresses, again, meaning you're going to be yielding earlier. So, and one way to handle this is that you just reduce the module's elasticity by the 80%. So instead of using 29,000, you end up using 23,200 KSI. And what this is going to do is increase the deflections of the structure and will increase your second order effects. And then lastly, also to make the adjustment on stiffness, there's an additional factor, and it's called the stiffness reduction factor, tau sub B, where if your axial load is greater than 50%, you then make the reduction by the formula that is given there by the bottom of the slide. And again, this concludes the brief introduction to the direct analysis method. Again, you're not liable for this in CVN 446. And so this ends basically Module 11.